Okay, I hope today is going to be more fun, like workshop. Also, the video hopefully will be much better. Don't worry about the previous video. I understand that the audio was not good and maybe homework was too difficult to fill. But anyways, so today we will cover significant topic with regards to the deep metric learning. So the deep metric learning, it needs also some way to, okay, I just realized that there was a little bit mute problem. So today we'll cover the deep metric learning aspect of that is principal component analysis. So often in the papers that you find where you have some like triplet loss, contrastive loss, or other types of deep metric learning, they use Euclidean distances, and Euclidean distances, when you have a lot of dimensions, do not work that well. Like with the cosine distances, you can imagine they are like angles between vectors, but if we think about the Euclidean distances, like when we increase the number of dimensions, the difference between 2 points at, let's say, random space starts to converge to some arbitrary value, and at the end, like there is not much difference between vectors in the space when you use the. So let me check. So when you use the Euclidean distances, and that's why we need to reduce the dimensionality. So let me check, did I share everything correctly? I think I did not share everything correctly. So yeah, so the distances okay. So the idea then is to use this Pca whitening. It's sometimes called, or there are actually some additional steps for whitening, but in general, this is dimension reduction, and then afterwards you can do the clustering. So maybe this image is not great, but you'll see in a second, and we'll code, and hopefully it will get more understandable. So the idea is that here you have three-dimensional space, and here you have two-dimensional space, and they are the same data points mapped, like projected on some arbitrary plane, where you have better separation between these classes. In this plane, you can see that, let's say, the cluster between the green and the violet ones are quite mixed up. In this plane, they are well separated. And you can think of that similar idea when you have like 128 dimensions and then you reduce it to 64 dimensions. We cannot display that thing, but still powerful way to try to eliminate a little bit of variance. So basically what it is just like the variance or standard deviation or some kind of how different are values depending on which plane they sit. So I will give some examples, and then we'll also look at equations. And when we start coding, you definitely get it the understanding better this concept. So and we'll actually use the same Pca technique next time when we'll work on clustering techniques with regards to that deep metric learning. So here again, one example that I got from internet. So here is the idea that you have two-dimensional data points, right? So every data point have two dimensions, y and x. Maybe I should need to make it even larger. And we look at the variance or standard deviation for every point with regards to some arbitrary plane that we want to project the vectors to. So we can project vectors to different kind of arbitrary planes. We can find those planes in different ways. We will look at some of the powerful and very simple ways how to do this today. So if you look at this example where every sample have two different dimensions. So the blue ones are the samples, and the orange ones in this case are the plane. So the orange ones, there is like kind of like a vector or plane where we want to project all of them. So the task here is to project points from 2D to 1D. By the way, if you have questions, then write in the chat. I will try to answer. So here the idea is following that if we project on this plane, on the orange one, we will get very nice separation because the variance on this plane, if you look at the points, like the length of this orange vector, this is much larger length than this green vector. And if we project on this vector that is actually placed here in the middle, or actually in this case it doesn't matter, it can be placed also here, but we will get the projection where all of the points are on this line or this vector or this plane nicely separated. Whereas if we would project on this green one, that also looks quite fine, because this is again all of the, like this vector and all of the points are kind of perpendicular, and you will see in a second that there is also a reason for that. And if we project on this plane those vectors, the result is not as good, because right now in these places there will be a lot of points clustered to each other. They will be like covered with each other, and we cannot really then decide to which cluster these points belong to. So I hope that at least in some way it gives some understanding of why this is useful, and how it, like in general, works, that you just need to find some kind of plane to project the vectors where there is the largest variance, so the largest standard deviation. So we want to project all of our data points, the blue ones, on some kind of plane or vector in this case, because this is just one-dimensional, where we preserve the largest variance of this data set. So if we achieve this, then we have this example as previous slide, where we have nice separation between the clusters. If we don't achieve that, the separation is bad. So that's one thing. And in order to achieve this thing, there is again interesting path to this. So this is okay. Let's do a small survey. So in the chat, so do you know? So do you know how to calculate eigen vectors and eigen values, and what they are? They are, so plus minus in the chat, please. So if you could give me some feedback in the chat. Oh, nice. So I see at least one person saying that he understands eigenvectors, so that's great. So if you understand eigenvectors, you might kind of see that in this case, the eigenvectors and the values are kind of useful. So let's see. I have some pictures that maybe I can show. So I see that one person is confident and others are not so confident about this stuff. So the eigenvectors and eigenvalues, they are two ways to describe some kind of transformations, and these transformations and they kind of, in this case, would quite correlate with the way how these standard deviations distribute in the dataset. But the idea is that eigen, basically, I think it was from Latin or some language, what means the characteristics or the kind of like some kind of, you can think of the vector that is kind of constant between all data points with regards to some specific transformation. And in this case, this is, I think there was, like in this example, it was quite nice that the red ones, if we have, for example, 4 points here of the data set that creates these rectangles, then the red vectors, those are regardless of the length, but they are eigenvectors, because when we change the size of this this rectangle, they always stay at the same direction. So that's why they would be called as an eigenvectors. And if you think of your data set, then also if you think about your data set on those situations that I just showed you, you could also think that you have some kind, those data points are kind of like edges, or like like not the edges, but the nodes of these rectangles. So let me try to emphasize that. So here, if you think here is some node, here, right? And we can apply some kind of transformation to those nodes. And if you think of there would be a lot of data points, we can also try to find where there is these characteristic vectors that are always same for this imaginary transformation. Like, it's not mathematically imaginary, but you can imagine that there is some kind of transformation to all of those data points that describes it. So in this case, these are very simple eigenvector situations where you have some data sets, and they are quite very nicely laid in this like they are not skewed, so they are not like in this kind of shape or some kind of like here and here and here. So they are very nicely laid. So one is a little bit more in this x-axis, and the one is a little bit more distributed over y-axis. And so the idea is that there is a mathematical process that we will just quickly look at it, that you can get these vectors out. So, and this vector itself, this is called eigenvector, and the length of those vectors would be called those eigenvalues. And here there is, like in matrix representation, the same idea. And of course, you can have the eigenvectors and the eigenvalues for all sorts of transformations in geometric stuff as well. But here we're interested of like describing with these vectors the idea of preserving the standard deviation or the most variance of the data set. And they fit very well for this task. They're really perfect for this task. So, don't worry about the mathematical process, how you can calculate those vectors and lengths. We will look at it, but let's ask some question now. So, do you get the idea so far? So, plus, minus, about the eigenvectors and eigenvalues. Eigenvectors, eigenvalues. Okay, great. So the idea is clear. Then we'll start moving to the actual calculation part. So let me try to pick up the LaTeX. So the calculation part is also not that crazy. If you have some kind of matrix, so I will try to add the equations to the Jamboard. So just a second, maybe I will also, no, I will just drop it. So there will be some, okay, let's use it C dot, there will be vector, and then there will be lambda, hopefully. just bear with me, I will drop the equation just in a second. C dot V, let's see, hopefully, yes, looks good. Copy, so Okay, let's see. So the the property and the mathematical way how we can get to that, basically the answer of what we were looking here, of those two vectors. So the vectors itself. So this applies to all of the dimensions, of course. So this can be used for the first dimension, second dimension, third. Like if there is 100 dimensions still. So the vector. So the vector is multidimensional. So these are. So here in this image, v1 and v2 is just 2 dimensions of. So sorry, I'm mistaken. So each there is going to be that many vectors as there are dimensions. So anyways, so and there the lambda is the length of those vectors, and A is this matrix that we want to apply here, and this can be any transformation matrix, basically, better linear transformation matrix for this equation to work. And actually to this A, in sense of these data points, you can use it as a covariation matrix. So again, the way how this works is you could use some other functions as well, but first of all, they should be linear transformations, and second, like the principal component analysis primarily works on the the linear one works with the covariation matrix. So maybe I should actually share the full screen, then you can see how I write equations. Just a second. We'll get to the coding very soon, don't worry. So let me share again the full screen. Okay, so now maybe it's a little bit better. We'll see. So yeah, there's going to be as many vectors as dimensions, or there's also a slight possibility if the A matrix is a little bit larger. So it depends on the size of the A matrix. If there is like three dimensions, you will see in the code that we are going to do, and the A matrix is actually like some other way calculated, not using covariation matrix. Then if there is 1,000 dimensions, then there is going to be 1,000 eigenvectors and 1,000 eigenvalues. That number depends on the A matrix. But the A matrix in the most simplest way is just the covariation matrix. So there are at least 2 ways how you can calculate covariation matrix. One is that, like I think you use in the economics and stuff like that, where you have like where you look at each of the pairs of the samples, right? You can look at every pair of the sample and then calculate the average value, subtract it, divide, multiply it, divide it. Well, the other way, the smarter way for mathematics is to use the kind of dot product here. So like if I'm not mistaken with the equation, it would look something like this. So okay, we should have I there. Just a second. So let's see, there's going to be I, and then there's going to be, and we'll code this just in a second. So C dot and XI. So this is, yeah, just the transposed one. So transposed one. Again, I repeat that this A matrix can be also something else depending on the situation. So I'm just showing the simplest version, and then we'll do a little bit smarter version. So, and this is actually covariance matrix in this case. So let's add some additional info here. Covariance. You can calculate it also another way, by the way. So that's one thing. And so then we need to kind of solve the equation. So the covariance matrix will have the shape okay, in this case, if this is a 2-dimensional example on the right side, then the shape of A gonna be 2 by 2 shape. It's going to be 2 by 2. That's one thing. Then the next thing is that we need to plug in all of the values and try to calculate from the equation, what is it called, the system of equations, the v and the lambda. Those are the two things that we need for this to work. So we need this one, and we need this one. And as funny as it looks like, it's actually possible to do. It's really neat equation, I think. So the way how you could do this is, let me quickly try to do this. So together, so c dot v minus lambda, and we're gonna call that in a second as well. And I think that could be for my students one of the homeworks, just to finish this tutorial in the Python. So so this would be the first line. So we just moved that part to the left side. So that's great. Then the other thing, so there's like two additional steps that are really clever. So somebody like a long time ago, I'm not sure who thought of them, but basically the one is that you just can put, if you have like some dot products, you can squeeze inside any dot product identity matrix, right? And it doesn't change the output at all. No changes in the output if I just add identity matrix. So that's fun. So we can add identity matrix. Hopefully you remember what is identity matrix. If not, you can type in quickly in the Google and you will see that. Okay, so sorry, here I need. Okay, so in this case I actually don't need that one, but I forgot the minus sign here. So okay, great. So I plug in identity matrix. It doesn't change anything so far, so that's great. But then the clever thing why so the plug in identity matrix is because the lambda itself is a scalar value, the length of the vector, right? So the lambda is not a vector, but lambda is scalar value. And if I have identity matrix here by the lambda, then this immediately becomes a matrix, lambda by lambda scalar value by the identity matrix, and that would be then subtractable from that other matrix. So again, the lambda is scalar value with regards to every v vector. Again, it's like a batch, you know. So anyways, and we can bring the v out of that equation. So that's again also easy part. Like everything so far very trivial. And then the next step also fun. I think, at least for me, I like the next step. So so far so good. And then the next step is that so you think about this equation. So only possible situation how this equation can be zero is either the first part of the equation is zero or the second part is zero. And we know that any eigenvector in our dataset representations cannot be zero. If it's zero, then it's useless, right? So we can say that definitely the first part will be zero, not the second part. And we can throw out the v, and that's really neat, I think. So we throw out the v, and then we end up with something like this. And then in order for this to be true, one way is to add the determinant, to calculate the determinant, basically. So we can the way how determinant is sometimes displayed is like this. So the matrix determinant, and basically we're almost ready for calculating the lambda. So the idea is that when you calculate lambda, then the next step would be to plug in the first equation lambda, and then you can get the v vector, the eigenvector itself, and then you're good to go. You have the vectors, and then you can project to the one that have the largest variance, right? But unfortunately, this is again not so simple, because if we think about it, so the unknown thing is lambda here, and depending on the dimensions, so if I write here dimensions of I shape in this case is going to be 2 by 2. So this actually would look like, maybe hopefully I managed to remember how to write this begin some kind of matrix. I think was like that. Let's see, there are a lot of types of matrices for the lambda for latex. I hope that this one is correct one. So then so this would look like when I multiply that by the identity matrix. Okay, except this is not what I want. Some kind of B matrix, was it? I think there was. So don't look really great. Just check me out. I will try to find what was the so latex matrix. But the idea is that so if I do the dot product with this kind of matrix that I will fix just in a second, I will get like quite complicated stuff because B matrix, okay, because those lambdas will start to be squares, depending actually also on size. There's going to be squares. There's going to be like at multiple places in the equation. So definitely by hand you can do this easily. Like by hand there is no problem. I think not easily, but you can do this by hand. Okay, so I don't like it yet, so I need the and. Okay, I forgot how to do this. So okay, now it's going to be fine. Okay, except the wrong place. Now it's going to be fine. Great. And so, but we will not need to do this because there exists some mathematical solvers of equations. So if I create this equation, just do that multiplication, not multiplication, but dot product and subtraction as well, then I would get equation and also the determinant. I forgot about the determinant. I would get quite interesting equation. So actually, just to make it quicker, I will give some maybe some screenshot of this stuff. And no worries, we're gonna start coding just in a second. So where was my screenshot stuff? Oh shit. Okay, this is not working like I wanted. Okay. So just to make sure that you understand, for two-dimensional stuff, we get something like this, where first of all we subtract that identity matrix multiplied by lambdas. Then we have the determinant calculation. If you remember, the determinant calculation is just by multiplying like in a cross section. So it's like you multiply in this way and you multiply in this way and then subtract them, and basically then you get that kind of equation that you need to solve. Of course, if you think in Numpy, there is linsolve or something like that, but there is again the square, so this will make it a little bit harder. And then you can get those lambdas. And when you have those lambdas, then of course the vector calculation is easy, because you can just plug in that equation in that previous equation. So just let me quickly share that one. So this one. And with regards to, so we actually today it would be much interesting to look at larger dimensionalities, not two-dimensional data sets. So we'll look at, for example, at three-dimensional data sets. And for three-dimensional data sets, it will be even harder to calculate, for example, determinant. Let me quickly copy that example. I somehow selected my images and I cannot unselect them. Invert selection. Doesn't work. Great. Apple, thank you. Oh man, I don't know what I did. Just a second, bear with me. I will copy nice picture. Okay, so for the determinant calculation for three-dimensional matrix is even more complicated. It's something like this. So you can imagine that this is doable. You can solve all of those lambdas and then get the vectors, but of course quite like a painful process. So that's why we're going to automate that process a little bit with Numpy. So that's one thing. So basically, we're already almost almost ready to do the linear PCA. So first step is then to calculate these eigenvectors and eigenvalues. Then the next step is that we need to oh, thanks. Some Normans was giving me B matrix and I did not see it. So, and then the next step is just that we need to like order in decreasing order or increasing order, or whatever. So so we need to sort the eigenvectors. Maybe we can even somehow display this stuff. Just a second. So you need to sort those vectors, and then we need to project basically the data set on those vectors. So we construct from those. If we have three-dimensional data set, we construct then two-dimensional projection matrix from those eigenvectors that are sorted in from the highest to the lowest. And then we project the dataset. So actually I have these steps, maybe because I was a little bit chaotic, let me write down the steps again, and then we're going to code those very quickly. And then I show you also some more powerful methods. Just a second. So the first step is, okay, let's call it so PCA. So for linear PCA, by the way, there are other flavors as well. Linear PCA. So one is calculate the covariance matrix. Then the second is compute vectors and the eigenvectors and eigenvalues. So the V and lambda. Again, I'll show you, like, and you probably know that there is a function that do this automatically, so you don't need to write all of this equation for the determinant, and this is like really painful, and I don't know, like, you could probably somehow try to code this, but not easy way. So then we sort the eigenvex by eigenvalues. So this is the equivalent of having the most variance of the vector as the best one to project the x's. So we calculate actually the covariance matrix from X, of course, from the data, right? Then we construct the projection matrix, projection V from eigenvalues, eigenvectors, sorry. Of course, eigenvectors. So, and then we do the dot product between the C dot between the X and display the data set. Basically, usually you just select those dimensions that you like. So the biggest variance at the end. So we'll do that just in a second. Hopefully it's clear so far. So I'm a little bit worried that maybe I was a little bit not consistent. So is it clear? Is the procedure clear so far? How to do the PCA? So to calculate covariance matrix, that I gave you equation. So then calculate the eigenvectors and eigenvalues, either using this complicated series of equations or using some hack function that I will show you, then sorting the eigenvectors by the eigenvalues so that we would have this effect of having the biggest, like the largest variance as our base projection vectors, and then just project the x to those vectors. So in general, not too difficult, but we'll see. Also in the code, I think it's not too bad. So just a second, I will share my code. Where was my code? And you can also open the PyCharm or some like Python environment, and we can code together. So we'll have some example here. Just a second. We'll use few tools. Just don't like I could do this like entirely from top of my head, but I'm a little bit scared that I will have too many bugs. But we'll do it mostly from top of my head. So there are the some dataset functions that we can use. So inside the sklearn, so let's see, we need the make blobs import sklearn dataset. Actually, we could write like that, from sklearn import make blobs. So make blobs, actually there are all sorts of nice datasets that you can use. Some are synthetic and some are actually kind of real datasets. I'm not sure, like California housing dataset, wine dataset, and stuff like that. So that would be one part that we need. So then, of course, let's add matplotlib so we can display all of this stuff. Matplotlib as pyplot as plt. So that's one. That's two. And then, of course, we need numpy. Import numpy as mp. And then we will need those extra nice functions for calculating I think it was in the numpy function. Do we need actually something else? Maybe we don't need anything else. Okay, so let's start working on it. So one is, let's lock the random seed to 10. So because the blobs will be a random data set, and I just want to make sure that every time I run, we have the same data set. So make blobs, and this will contain 1,000 samples of n features. Let's start by two-dimensional, then we'll go to three-dimensional. So then 3 clusters, and what was the center box by default? Sorry. Okay, we can leave it as that. So that will be fine. Then the next thing is, then we'll plot it. So plot. There is a plot called scatter. So then the scatter will just display all points in 2 dimensions. You cannot actually plot, I think, in 3 dimensions with scatter. Definitely, maybe there is something. I think there is some way. I remember there was some 3-dimensional stuff as well, but so I did not check it before the tutorial, so sorry for that. So here, then we can plot all of those samples. So for example, first dimension, we select all of the samples for first dimension, then we select all of the samples for second dimension, then we color them by the index of the cluster, and then we plot show them, right. So I also want to close all of my experiments before, and if I run it now, hopefully it should work. Yes, so we get quite nice clusters. We could probably try to make them a little bit more noisy. I think there was a standard deviation, sorry for little bit disrupting. So we can add cluster standard deviation. By default, it was, by default, cluster standard deviation is 1. So let's see what happens if we add it as 2. So it will be quite a large jump, I think. So we'll see. Okay, now they are a little bit more like covering each other. So probably those two might be actually, if we do the spectral clustering or something, they would definitely be as one cluster, the two of those lower ones. So that's so far good. Then the next step, we will try to do this with 3 dimensions. So let me check. So let's see. So if we add 3 dimensions here, then basically, maybe this would actually work. Also, probably it will work with 3 dimensions, but not as good as we could. So actually, not that bad as well. Funny enough. So if there is even more dimensions, then it should start looking not so good. Let's see if we have standard deviation of 3. Okay, now they are like much more overlapped. So we're just looking at only 2 dimensions, but actually there are 3 dimensions. That's why I was checking out that. So let's start then applying the Pca algorithm. So linear Pca. So that's great. So let's start first by covariance matrix. Also, there is a slight thing that you could like these blobs, they are centered around the kind of around the middle of the, like around 0, 0, but there could be situations when the dataset is not centered, then you need to center it first before trying to calculate the covariance matrix. So of course, maybe it also would benefit in this case. We'll see. So we should do the so let's see, 1 divided by 1000, so that is the number of samples, and then we can do the NP transpose of the x and then the dot product with x, so something like that. Then the next part would be calculating the eigenvalues. So here, to avoid all of those determinant equations, there is a nice feature in the Python called linalg like an eigen, right? So we can give the covariance matrix to this function, and then we get lambda. Actually, you can write it lambda. No. So if you write the lambda, then it will think that this is a Python lambda. Okay, Christopher is asking about this one. So this notation is some like an operator that Python can override, and Numpy has overridden this with np matmul. So that's the same operation. So if you look inside, I think Numpy code somewhere, you can see that it overrides operator if you work with Numpy arrays and just use this function. So you can use that function as well. It will not be exactly the same result. So that's one. Thank you for asking questions. So then the edx's, so the indexes. So we can then sort our vector. So as I said before, okay, if you have here the 3-dimensional stuff, so that means that the covariance matrix will be 3 by 3, 3 by 3. Then the these stuffs will be then. So the covariance here is then the lambdas will be just 3-dimensional. So there will be 3 scalar values, and the vectors will be again, I guess 3 by 3 most likely, like that. We'll check that, but I think it should be like that. So then arg sort, so we can sort arg, so we can get the, so this is like sorted. You can actually do sorted as well probably, and then you need somehow to like zip together indexes. So this is just giving me the in the ascending order indexes of array. So, but actually that is the sorted by the value. Indexes of the array is sorted by value. Okay, that's great. So then we can double check if this function is okay. First of all, you can just like resort the lambdas and then debug it and see if it's great. So, and then we can also sort, of course, the eigenvectors as well with the indexes. So that's also great. So, and then we need to project basically, and let me think. So there is a three-dimensional. Okay, I think there are like usually people just project and then select only dimensions that they want, but probably we could also create first the projection matrix and then we don't need to care about dimensions, but let's do with the first option. So with the first option, this will be x projected. So x we can project directly on this v because the like kind of these vectors are stacked together and they are like a matrix basically, and that's why you can project to that one. So that's great. Then we can do the same idea as before, xp. But now, because this was ascending order and we want actually descending order, we want the most variance as the base vector of the projection and the least variance as the last vector. That's why we need to have -1 and -2. If we would have 0 and 1, then that would mean that we will select the worst vectors to project. So let's see how this works. And if this works, I will drop the code also on the Jamboard just in a second and let you get along. Okay, so now it looks good, I think. Not maybe like that excellent, because still these are just 3 dimensions. You cannot actually have like huge difference, but let's see. So, and if I try to project the worst ones, so let's see what happens if I try to project the worst ones. So yeah, so with the worst vectors, there is like complete overlap, and this is not what we want. So we want the best vectors, so those are the last ones. So if we project on the best, with the largest variance, so here the first ones are with the smallest variance, so now we get nice picture. Okay, so this kind of works. I will drop this to the Jamboard. If you have some problems, something not clear so far, let me know. So we already did like a proper like linear PCA, like the one that is like you can reduce the dimensionality by projecting on some linear, like in everything here is done in a linear manner. You can also probably invert a lot of things here. So the one is that this is very nice feature for deep metric learning, because when you need to calculate the sizes of the clusters, the clustering of some kind of things that are not yet for the data points that were not included in the original training set, it's better that there is no additional non-linearity, because already the model is quite non-linear. If you add even more non-linearity, this is like really unpredictable stuff happening. So this is very predictable, very nice way to try to reduce dimensions. So I did not try it before, but I think if I increase the dimensionality, like adding 8 dimensions, it still should work. It should work, hopefully. Hopefully I don't have some bug in my stuff. So now the projection doesn't look really nice, but still it kind of, at least there is no bug. So the projection of these looks like that, and if I'm trying to look at the worst ones, let's see what will be the worst. So the worst ones are even worse. So with 8, it's a little bit better, but not great. I guess, so here I think we have some limits. So I mean, with linear projection, there are also some limits. So if the clusters are too overlapping between each other, there is no way I can have the linear projection that will separate it nicely. So if I try 4-dimensional stuff and try again with 4 dimensions and see this was the best ones, the worst ones, so you can see quite nicely the difference again. So where was so I added in the Jamboard, by the way, this stuff. So this is the worst ones, and these are the best ones with 4 dimensions. Let me run again. So again, this is not perfect, but better than the worst ones. So basically, what I'm trying to say is that linear projection is predictable way, really nice for deep metric learning. At the same time, if there is too much of overlap between those clusters, it will not work. So then let's move to the other part, because I don't want to make this too long today as well. So I will go back to the Jamboard. By the way, in the Jamboard, you have the code. So where was my Jamboard? Hopefully, so far, quite fun, because you can imagine that, you know, like if you have like high-dimensional data input, for example, you can map this in this linear fashion already. So to have a little bit smaller, like the easier problem to solve. So this is one thing. So I already started seeing some problems when I increased dimensions, right? So if I increase dimensions, we're starting to seeing situations like these. If I try to project down to the 2 dimensions just with linear projection, I get something like this, where the points are like clustered together, but at the same time you can visually see that theoretically these could be separated. For example, if I somehow could extract this part like in some kind of z-axis out, and then these down, and then kind of try to project them on some arbitrary plane in between, this could work. And in that case, we could use also some other ways of the principal component analysis. And the one way is that we could imagine that we could project this kind of these x's on some kind of arbitrary plane that is like dimensionality that is much higher. So for example, we have the 4-dimensional input, but we want first pass them through, let's say, 128-dimensional input, and then calculate covariance matrix, and then choose the projection from that. And the phi here in this equation, so this is actually called kernel. You will see that this is called this kind of Kernel Pca, but basically here the phis are some kind of function that projects the x from low dimensional space to very high dimensional space. And by the way, we don't need to calculate that out, because there are quite a lot of like proofs, and this is really also, again, the second time I say today, very nice, smart, clever mathematical stuff, where you can prove that if you have some kind of covariation matrix, so this is just for this specific case, where you calculate covariation matrix, and if you have some kind of high-dimensional function here, then in that case, if we put any high-dimensional function here that is not linear, you will also get that the same output can be calculated directly as applying the kernel function. So if you have just a squared here between 2 dimensions, and either or having the dot product with the passing to the phi that also do the squares, and with the transposed here, you will have the same output as you would do that just by transposing and squaring that output. So you kind of eliminate immediately the fees, so you don't care about this actual operation of like again calculating out all of those fees to each of those, then transposing, then having the dot products. And that's called kernel trick, that basically you can prove that like doing those functions for every of the dimensions and then doing the transpose and dot product is the same, exactly same output as you would just do the transpose and dot product and then do the same operation, both of them. So you save the computing resources and make the equation a lot easier. So, and then a lot easier equation is basically this kernel function. And the kernel function idea is that you just apply the same function many times for each of the pairs, and then you get the same effect as that would be as the covariance matrix. So these, in case of this high dimensional value, so if you have this kind of phi that is, it doesn't care what it is, basically it can be a squared function, it can be something else as well. And you will see just in a second that there is actually better ways to do this. So these two are the same, when you try out mathematically different kind of phi functions. So that's called the kernel trick, and that's why quite an efficient way to make it easier. So that's one. Then the last piece of component to achieve this nonlinear Pca projection is that we need to choose the kernel function, so that phi function. And that phi function, one of the ones that usually are used, and also we will see in just in a second, is called the radial basis function. I don't want actually to write it down. Maybe I should. No, don't know why it's not opening. I had prepared it before. It's kind of not opening yet. We'll try again. If I cannot open my equation, then I will need to rewrite it on fly. I don't know why can I not open it? Okay, just a second. I will screenshot it from different part of my screen again, and then we'll implement that quickly. So the kernel function of the radial basis function. So the radial basis function actually also a very popular function. You can use that one. So I have, like in the early days before the deep learning, that was one of the go-to functions for like having these non-linearities for the models of machine learning models. And the idea here is again very simple. So you already know from the deep metric learning that this part of equation is a pairwise distance of basically this can be Euclidean, cosine distance, whatever. So then the gamma is hyperparameter. So this is again making this a little bit nastier function than the linear Pca, because gamma is something you need to find. Again, it will not work good with all of the gammas for every dataset. And then exponent is just an exponent. And so this is a kind of highly nonlinear function that you can apply for each of the data points and like the actually pairs, and then you can get basically use that as a covariance matrix and then follow almost the same steps as before. So okay, let's move back to the code, and then basically we'll have few parts of the code, and I guess that's going to be it for today. Hopefully it will be fun enough so far. So at least these tools should give you quite powerful ways to visualize things, to build models and stuff like that. So, and by the way, if you have some questions, you can write in the chat, of course. So what I propose to do is to copy this code, so I don't like smudge my linear Pca. I just want to make another code. So another code, another file, and just copy everything that I had before. We'll do a few small changes here. Hopefully it will work, and then we'll see. So Let's see. So the covariance matrix, we can now replace it by that idea of having the kernel function. So the kernel function, let's see. So we can have the NP of exponent, right? Minus gamma. Gamma will be hyperparameter. So this will not be linear anymore. This will be kernel. Kernel Pca gamma, we can set, let's say, 1, e minus 1, maybe e minus 2, we'll see. So that's one. Then if this is just a scalar value, I can multiply it. And now it would be nice to have some function where you can calculate pairs between each of the data points just in one function. And that function, of course, is called the PAD_dist. And we can get PAD_dist from the Cpi, I think. So from, I'm not sure, maybe, yeah, Cpi, I guess. So was it spatial distance, Pdist, and then also, okay, let's see, Pdist. So we'll check the shape of that one. So Pdist of the x, I think it will not return it as a square matrix, but let's see. So if I debug it, by the way, Pdist, the default metric is Euclidean. So so the metric is Euclidean, I think, Euclidean. Maybe it would be fun to try cosine distance as well. So let's see. So, okay, so the covariance matrix or the pairs, so the Pdist, I think in Torch actually the Pdist works a little bit nicer. In Torch it returns back the just like symmetric square matrix. Here it returns back like the flattened matrix. So flattened matrix is not cool. So we don't need a flattened matrix. So square form, we can use this kind of function. I think you can do reshape as well, but I'm a little bit scared that maybe it's a little bit different. I need to check how the square form works. So here we can use the square form of covariance. So reshape, basically this is basically reshape from flat to, so this will be then most likely 1000 by 1000. No, let me check. I think it should be 1000. No, but there are 4 dimensions. Let's see. So each pair covariance, yeah, it is 1000 by 1000. Why was starting doubting myself? So anyway, the distance between each of the data points, right? So like the pairs of all of the data points. So that's our kind of a covariance matrix. At the same time, it's not really covariance matrix, it's just from the kernel trick extracted that we can use kernel function skipping the actual covariance matrix calculation, and this is the same value. So that's one. Then we include inside this part so far, like that. And then we could project on that. So about the projection thing now, I think we should, the difference here is now, because this is actually not a projection matrix anymore. I'm not sure about this equation, so let me run, but I think we should not project it actually for the kernel function. Okay, yes, it even don't work here. So for the kernel function version, at least in the implementations that I have seen, they use directly just these vectors here, the eigenvectors, but basically the eigenvectors here are also a little bit tricky because they are actually not really any more linear like projections of the data points. If I have the breakpoint here, they are now something a little bit different, because they are those pairs of every data point in your data set. So let's see, the V, V shape, yeah, so the V shape is 1000 by 1000. So that is actually the vectors itself are now containing the data points, but in this eigenvector form. So if I try to look at the output, so previously we constructed the projection matrix and projected the on those the data points, but now they are containing it themselves. So this looks a lot better, I think, than before. So let's see if I try to change the gamma to something else. So E minus 2, okay. So this is not better. Let's see, so 1, gamma 1, maybe something larger. Okay, very interesting result. So 0.5. Again, so now you see that this process is not as simple as before. It can work. It can sometimes also not work. So I guess something like this is better. But let's see. Can we use cosine distance? I'm not sure about that actually. So maybe it will not work. Need double check the math before doing something like that. Okay, no, it works actually. Yeah, you could probably with cosine distance you also could get something really nice because they have the kind of cyclic nature. So okay, great. So I will add this also to the Jamboard. So for my students, I would like that you try to implement this stuff by hand, and maybe even play around and try some other kernel functions, because of course this kernel function for the the kernel function basically is where you look at the pairs for all of those x's. So, and you can have different kind of those kernel functions. The idea is that it is not linear, and then when you calculate those eigenvectors and eigenvalues, you try to find those that contain the most of the variance. So let's see. So if I add this to the Jamboard, and then we'll do the last example today. So the last example that I want to do is I will copy again the code. I'll suggest that you also do. And actually in your deep learning projects and also with deep metric, you probably don't want to implement this by hand. Otherwise, like for the kernel function, maybe you want to have some kind of very specific kernel function that you understand how it works like and stuff. Actually, like it's always great to understand how this stuff works, because otherwise you think this is magic, and actually this is not magic at all. So the one way how we can also do the same stuff is using already pre-built models of, like, they are not actually models but the same algorithms as we did before. So I think they are located in sklearn, yeah, and decomposition, right? Import sklearn decomposition, and here we can try out different kind of them. So that's why I was said in the beginning that principal component analysis have different like flavors. So we can use the most simplest one. Oh no, the autocomplete doesn't work. Okay, hopefully there is a PCA. So this is one PCA algorithm. Then n components, components. Maybe I have missed something. Hopefully not. So this means how many components do I want to project? This -1, -2, and actually, so in this case I can leave it as that, but it doesn't care actually. So PCA of that one. Then we can do the so this is actually the V, but we can have the XP, so X projected, and this can be PCA fit transform. Very strange that I don't get the autocomplete. Hopefully there is no bug. Let me check. Of the fit transform of the X, and then Let's see. So let's see. By the way, there is another interesting thing. The projection matrix, of course, you can use for different kind of vector data points that were not included in the original eigenvector calculation. That's why it's called fit transform. You can also have the fit. Oh, Christopher is saying that in previous example 0.25 looked good. So the idea is that you can fit it once and then use for many other types of data points. In some cases that also is important. For example, if you calculate the radiuses with a deep metric learning model of some kind of embeddings, and then you apply this PCA transformation, then of course you want to apply the same transformation for new data points to calculate the same distances, not some calculate a new PCA with the previous distances. So that's why you would want to fit it once and then transform it, because there is actually also a function called just PCA fit, and then there is also a function PCA transform. So that's one idea that's useful. Also, I want to check that the shape is 1000 by 2. It seems okay. Okay, so it seems okay. Let's see. So if I run it till the end. Okay, that's nice. The output actually looks quite similar to what I had before. So yeah, so we can project it linearly. So this is a linear PCA. Then we can also try this kernel PCA. That was what we just implemented with Radial basis function. Again, the fun thing. So kernel PCA, I really don't like that I don't see autocomplete. I need then to look in the documentation. So the kernel PCA also have default value, right, in the parameters, and if you don't understand how it works, you just leave it as that, and then you think why it's not working as I want, because there is definitely must be gamma. So yeah, there is a gamma there. So gamma by default it's calculated 1 divided by n features, and that's actually fun that Christopher's told that in the 4-dimensional stuff it actually was that one was best one. So that's really interesting. Christopher's just discovered the formula of sklearn. There definitely must be some mathematical backing for that formula. So in sklearn, it is 1 divided by the dimensions of 4 in this case. That is default value, but that's really fun. So, but again, there is no magic, because you already see how the kernel PCA works. What is the pairwise calculation and stuff? There's nothing that difficult. So again, the output looks almost identical as before, but the nice thing is that we can change the gamma here and probably see something different. Okay, I don't see that much difference. Maybe I have some bug. Let's see. 0e minus 3. Let's see. Okay, I still don't see difference. Very strange. Maybe I run I run the same correct sample. Okay, we'll see. Let's try some large gamma. Really strange that it doesn't change that much. Okay, I don't know what's happening, but still, like the calculation that Christopher's gave is correct. It's divided by 4. That's one that they use in the sklearn, but you can use others as well. So that's one. There are also a lot of other types of PCAs. So one is called Sparse Pca, I think. Sparse. There are some of them are actually with a stochastic gradient descent, where you try to map something as well, like not map, but optimize these planes and try to get these projection planes as best as they can be. Maybe actually, I'm not sure. Maybe these functions also do something of that. That's why always they come out as the same output. So maybe if I increase the dimensions, Again, very easy procedure, right? You don't need to write those equations. You kind of understand how they works. So let's see. Okay, with sparse Pca with 16 dimensions, you get something more interesting. So, anyways, like these other types of PCAs, they are not really, mostly they are not linear. I'm not sure it's 100% if all of them are not linear, but most likely they are not. Incremental, let's see this one. I don't know about this one. You could check out also documentation of what kind of kernel functions do they use. So let me check what else there was. PCA, principal component analysis, incremental, mini batch, right? Mini batch is definitely something that you do some kind of optimization there. So PCA, there is a solver. Linear, yeah, this is a linear. So the simple PCA is linear. Also, there is a parameter actually called Weighten, where you have multiplied by square roots of n samples element-wise. So, yeah, sometimes you can use also parameter Weighten. Let's see. We tried, so the Weighten is multiplied by square root of n samples. Okay, that will give nicer results, but let's see what happens if I return to 4 dimensions. Okay, still the same output. Okay, that doesn't affect much because they are already quite centered and quite similar. Okay, so that's about it for today. Yeah, I will add also these examples to the Jamboard. Then I will prepare maybe a small homework for my students. Others can follow up on the Jamboard as well. And next time we'll work on some of the spectral clustering probably. So as now we know how to reduce dimensions from our cool deep metrical embedding learning models. The next thing is that we need to somehow calculate which class or how many clusters there are. And the most fun situation is when you don't know the number of clusters that you have, and we'll do that. We'll at least start to do that in next time. So that's it for today. If you have some questions, write me to the email. Hopefully it was interesting and useful. So we'll see you next week. Okay, bye bye.